So good afternoon, everyone, and welcome to today's seminar titled Computationally Predicting Better Dopants for High Mobility Transparent Conducting Oxides. It is a pleasure for us to have as our speaker today Professor David Scanlon from the Department of Chemistry of University College London in the UK. Professor Scanlon completed his undergraduate degree in computational chemistry at Trinity College Dublin in 2006 and his PhD in chemistry also at Trinity College Dublin in 2011, working with Professor Graham Watson. He won the Royal Irish Academy Young Chemists Prize in 2011 for the most outstanding Irish PhD thesis of 2011 in the area of chemical sciences. He then moved to the UK to take up a Ramsay Fellowship in the Department of Chemistry in UCL, hosted by Professor Richard Catlow, where he has been ever since. He was appointed as a lecturer in 2013, promoted to reader in 2016, and to Professor of Computational Materials Design in 2018. He was awarded the 2015 RSC Harrison Meldoda Memorial Prize for the development and application of computational techniques to understanding and predicting the properties of functional semiconductors for energy applications, and was made a Fellow of the Royal Society of Chemistry. In 2018, he was awarded the UCL Student Union Student Choice Award for Outstanding Research Supervision. Following this, he was shortlisted for the Times Higher Education Awards 2018 for Outstanding Research Supervisor of the Year. In 2021, he was awarded the RSC Material Chemistry Division Early Career Award for his work on conducting oxides. He has published over 240 papers in his career, and he is currently the lead editor for the new journal PRX Energy. Professor Scanlon, thank you very much for being our speaker today. Over to you.
Thank you very much, Stelios, and thank you very much for the invitation. The first thing I'm going to do is I'm going to stop my video because my internet is being slightly sketchy today, so I don't want to just stop in the middle of the talk. So can everyone still see my screen? Everything's still okay? You can hear me?
Yes, we can, thanks.
Perfect, okay. So today I'm going to tell you a little bit about our work on transparent conducting oxides. I'm going to show you the interplay of our calculations with advanced synthesis and characterization. And hopefully I will convince you that when you put these things together, that you can really do some compelling science. My slides are, there we go. So at UCL, I lead the materials theory group. We've grown quite rapidly since our inception in 2014 to now. This is just a selection of people that I managed to take to a lunch in October before we shut down again for COVID. There's 31 people in the group now, but we only got a subset of people here. I have people who work for me that I've never actually met that are based in Ireland, based in Singapore, based in Korea. So we're hoping that once COVID goes away, we can bring everyone back together to the one building, which would be amazing. But until then, we muddle through with online only working. But the group is mainly interested in looking at structure property relationships in the solid state, and particularly in regards to materials for renewable energy applications. So we have a focus on solar cells, on batteries, on thermoelectrics, and also on these transparent conducting oxides, which are, they make up a part of a solar cell, but they're also used in a lot of electronics, such as the devices that you're probably looking at this talk on. So why do we care about TCOs? Well, basically, they're everywhere. They are ubiquitous in our modern life. They're in liquid crystal displays. They're in the touchscreen in your phone. They're in smart glass, this low emissivity glass, and they're nearly in every single solar cell. So you can't really get by in modern technological life without having the use of transparent conducting oxides. And the majority of transparent conducting oxides that are used are actually N-type in nature. So they conduct via excess electrons. And P-type transparent conducting oxides are currently not at a level where they can be used in industry, only N-type are. That's a completely different topic and would take an hour to explain. So today we'll just focus on N-type transparent conducting oxides. So they're typically materials that are optically transparent. So that means they have optical band gaps greater than 3.1 electron volts. And by optical band gap, we mean the excitation energy needed to excite an electron from the valence band maximum, or the HOMO, to the conduction band minimum, or the LUMO, of these solids. And typically the oxides that we're interested in are zinc oxide, tin dioxide, and indium oxide, which you can see all have large fundamental band gaps. Once your band gap is greater than 3.1 electron volts, then light cannot excite an electron from the valence band to the conduction band. So light will pass through your system, meaning it is optically transparent. For really good N-type transparent conducting oxides, your excess electrons in your system will actually occupy the bottom of the unoccupied conduction band, filling it up with electrons up until this green point here, which is the Fermi level. So essentially your optical band gap becomes the EG, which is the fundamental difference between the valence band maximum and the conduction minimum, plus this EG-MB, which is the Moss-Bernstein shift, giving you the total optical band gap. So you can basically take a material that might not have an EG bigger than 3.1 electron volts, but you can dope it to make it optically transparent. Of course, there's issues with this because now you have electrons in the bottom of your conduction band, and as light hits your material, it could excite these electrons into other low-lying unoccupied states. So the next caveat is that we normally need to have a large separation between the conduction band and the conduction band +1, or the next lowest unoccupied state. And typically, these systems display very good conductivity, so carrier concentrations greater than 10 to the 20 per centimeter cubed, and conductivity is as high as 10 to the 4 Siemens per centimeter. Now, the conductivity of a typical metal is about 10 to the 6. So at 10 to the 4, you're here at the conductivity of a poor metal, but still very unusual to have high conductivity in a material that is transparent. So I like to show these pictures when I'm lecturing undergrads, because on the left is a concert when I was young where people used to go and dance. And on the right is a concert now where people go and film. And everyone that films at these concerts, they're using a device with a transparent conducting oxide in the screen, and they're also using a device with a lithium-ion battery. So it normally motivates two of the strands of research in our group. So of course, conductivity in these types of solids is controlled by defects, be they intrinsic or extrinsic. And we normally characterize these types of defects in these systems into 3 different groupings. So you can have a deep defect. That's one that is very, very far away from the band edge. So it has to be excited to get an electron from the deep defect state to the conduction band where it could be mobile. A shallow defect is one that is quite close to the conduction band, so that it only needs a small amount of energy to be excited. And we normally define shallow as being less than 0.03 of an electron volt, because at that energy range, you're about the 0.03 electron volts is about kT. So you will have appreciable conduction at room temperature. And then resonant defects are when the donor states actually sit high above the conduction band minimum, meaning that the electrons are injected directly into the conduction band. This is ideally what we want in a good transparent conducting material. So for N-type transparent conducting oxides, we need donors, so things that donate electrons to the system. So these are, in terms of intrinsic defects, these can be oxygen vacancies or cation interstitials, or we look at donor dopants, so a dopant that has one extra electron than what it is replacing. We also want to avoid materials where p-type defects are present in high concentrations, because of course acceptors will kill your excess electrons, killing your N-type conductivity. But we also need very good dispersion or curvature of the band edge. So the curvier your conduction band minimum is, the lower the effective mass, the higher the mobility of the charge carrier. We know from simple physics that conductivity equals mobility times carrier concentration. So the more extra electrons you can get in there and the higher the mobility, the higher the conductivity you will have. So we spent about 10 years doing this. I've been working on transparent conducting materials since my PhD. And normally people will advise you to go and change your research field slightly when you do a PhD to go and do a postdoc, because no one will hire you if you can do what your old supervisor used to do. But I never listened to that because I fell in love with TCOs. My wife gets very annoyed when I say that. But it's really been the research love of my life. And even after spending so long working on these systems, just when we thought we understood them fully, we came across a new behavior, and that's what we're going to talk about today. So typically, when we look at the band structure of these solids, so a band structure is effectively the MO diagram for a solid, just in 3 different dimensions. Normally, these materials have very dispersive conduction bands, and here we have the band structures of indium oxide, tin dioxide, zinc oxide, and barium stannate. So you can see that we have in orange the conduction bands, the unoccupied states, and in blue the occupied valence band states. The conduction bands are very, very curvy. They have very low electron effective masses, meaning high mobility. And they also have large separations between the curvy conduction band minimum and the next lowest lying bands in nearly every case. As I said already, most of these materials have these large fundamental band gaps, which means that they are already transparent even before you start doping. But you can make a small band gap material dope. You can dope a small band gap material to make it more transparent. You just always have to be wary of this caveat of the extra 3.1 eV separation needed to the next lowest conduction band minimum. So currently the field has a massive over-reliance on indium. So the TCO market is growing hugely. It's a $1 billion industry, but currently it's dominated by tin-doped indium oxide, which we call ITO, and amorphous indium gallium zinc oxide. So any kind of thin film transistor display or transparent display normally is dominated by tin-doped indium oxide. And because of this, the net demand is increasing as people are buying more and more devices. I mean, I currently have 2 tablets and 3 laptops, so I'm adding to this problem myself. But what this has done is this is made worse by the fact that indium is considered quite a rare element, and it is often found in places that you would consider to be geopolitically unstable. So if your local warlord has all of the indium under his control, then he can let it into the market however he likes. And this causes large fluctuation in the cost of indium over the last 20 years. And this has created a problem for industry because industry would love to be able to set their profit margins, and they could even accept a small increase in the indium cost year on year because they could fix that into their margins. But not being able to predict how the indium price is going to fluctuate is quite awkward. So this has made this large need to replace indium with an earth-abundant alternative, or at least to reduce the amount of indium that we're using in devices. So in terms of what we do in our group, we think that there's 2 open questions. One is, are there alternative TCOs out there that we haven't discovered yet? And are we getting the maximum performance out of the current TCOs? And the plan of attack that we have is we've been trying to identify better dopants for the current TCOs, which surprisingly no one had done up until now, and also trying to identify alternative wide bandgap oxides that could be TCOs. Now, today I'm only going to get to talk to you about the first plan of attack. The second plan of attack is also proving fruitful. We've now predicted 3 new transparent conducting materials that we've realized in the lab. So we're going in the right direction, but we can't release any of this yet because none of that is patented. So maybe the next time I come back to give a talk, I'll be able to share all of that results with you. So today we're going to discuss trying to find better dopants for the current TCOs. So conventional doping strategies are the same as you would use for doping semiconductors like silicon. Typically, if you have a material like tin dioxide, where you have 4 plus tin, and obviously oxygen is 2 minus, you would go 1 to the right in the periodic table, replace tin with antimony 5 plus, and you would replace oxygen with fluorine 1 minus. These atoms have 1 extra electron, so you're n-type doping your system. But because they're side by side in the periodic table, they're about the same size, so you don't have too much of a strain problem. They should fit in the site that they're replacing. Similarly, if you think of zinc and oxygen, for zinc oxide, you could go 1 to the right for zinc, and typically gallium is the best dopant, or you can go 1 to the right to fluorine again. But it appears that people for generations have used this kind of conventional doping strategy, and it has worked. And it worked for tin-doped indium oxide, it's worked for gallium-doped zinc oxide, and these systems are used in devices. But nobody sat back and said, is this the right approach, or are there better dopants? And are we maximizing the performance of these materials by choosing these dopants? So back in 2015, the dean of the chemistry department and the MAPS faculty came to me and he said, we've made some thin films of molybdenum doped indium oxide. We would like you to do some calculations to help us understand what's going on. And when the person who holds promotion in your university in their hands asks you to do something, you say, yes, sir. So we did some calculations, and we also had a quick look through the literature. And what we realized was that people believe that in indium oxide, where indium is 3+, molybdenum was thought to be incorporating as molybdenum 6+, donating 3 electrons per dopant. Now, this didn't sit well with us, because normally if you have a system where you're donating lots of extra electrons per dopant, you get killed by something called ionized impurity scattering, where all of these extra electrons are zipping around in your material, colliding with the actual atom that they've come from, and this causes ionized impurity scattering, which lowers your mobility. So we did some density functional theory calculations, we did some XPS experiments and some XAXS experiments at the diamond light source synchrotron, and we showed that it's actually molybdenum in the 4+ oxidation state, which is a 1 electron donor, meaning that it acts quite similarly to tin doping in indium oxide. So in ITO, tin is 4+, so adds 1 extra electron. And in this system, which we're calling IMO, obviously it's a 1 electron donor also. But from our analysis of the mobilities of the chemical vapor deposition grown films from UCL, what we found was that IMO was actually continuously being found to be better than ITO. And in fact, these results were actually breaking what we call the ionized impurity scattering limit. So they were breaking the rules that we had for conventional doping in transparent conducting materials. And we couldn't really understand why. So we wrote a large grant proposal to the EPSRC, backed by one of the biggest glass companies in the UK, because they were interested in understanding how they could make better transparent conducting coatings for the glasses that they sell. And we actually did a large amount of research into molybdenum doped indium oxide. And we found that there were about 30 papers in the literature at that point. And we added all that data onto our own data from extra careful growth surveys that we did. And what we saw was that actually IMO has a much lower resistivity or higher conductivity than ITO. It possesses a higher mobility than ITO. And this is across the board. Every single sample for sample, IMO beats ITO. Now, this is a shock, because there's famous papers out there. Klaus Elmer wrote a paper in Nature Photonics in 2012 saying ITO would never be beaten. So here we have the proof in the pudding that it has already been beaten. And we've known about it for a while, but we've ignored it. So it appears that the field of TCO research and research in general just treated these molybdenum doped indium oxide papers like a weird chemical curiosity. They didn't believe it really. They weren't going into the top level journals. And I think people thought they were just wrong. So the question for us was that, as both dopants are 1 electron donors, why do you have very different behaviors? So what's different for molybdenum than for tin? So this was an open question. So we also looked at the optical transparency of these systems, and what we can see down here is that they're pretty similar in terms of their UV transparency, but in terms of the IR transparency, the IMO samples are much more transparent in the IR. So this is definitely saying something different is happening when you incorporate molybdenum compared to tin. We can calculate something called a Hackett figure of merit, which is simply the transmission to the power of 10 over the sheet resistance. And what we showed was for very thin films of IMO, you could actually get much higher figures of merit compared to ITO. So all in, IMO beats ITO hands down. So we went to our colleagues in Liverpool, Professor Tim Beale, and we asked him, could he do some analysis, because he's a very learned colleague when it came to understanding free electron transport in oxides. And what he did was, excuse me, he fitted the optical bandgap versus the plasma energy for these systems. And he could fit the IMO data with a rigid effective mass or curvature of the conduction band minimum of 0.22 times mass of the electron. But when he tried to fit the effective mass for the ITO films, he had to actually use an effective mass that incrementally increased from 0.22 to 0.40. So what this seems to say is that incorporation of molybdenum doesn't change the effective mass of your conduction band, but somehow incorporation of tin does. So this was definitely a new idea in the field. So what we did to understand this was we can do calculations using our using the VASP code. So we run these on the national supercomputer in the UK, the Archer machine, and now the Archer 2 machine. So indium oxide crystallizes in this lovely cubic Bixby structure. It has two very different indium environments. Both are 6 coordinates, so octahedrally coordinated. But the 8B position, this purple one down here, is quite a regular octahedron, and the 24D site is a very distorted octahedral site. So when we calculate the formation energy of defects, we normally plot them in these types of diagrams. So on the y-axis, you have formation energy of the defect, and on the x-axis, you have the Fermi energy, which ranges from 0, which is the valence band maximum or the HOMO, to this orange line, which is the position of the conduction band minimum. And then this goes up just slightly above the conduction band minimum because we wanted to see where these types of dots appeared. So if you look at this is the formation energy of a defect versus where it actually, the defect states will be positioned in the bandgap. So if a defect slopes upwards to the right, it's an N-type defect. If it slopes downward to the right, it's a P-type defect. So what this tells you that is under oxygen poor conditions, the formation energy of the N-type defects is much lower than the P-type defects, meaning that the material is N-type. And also under oxygen rich, it is still always N-type until you get to this point here, far above the conduction band minimum, where P-type defects would start to take over. So this material is very easy to make N-type. Tin, shown in red, is a very low energy dopant, and it injects electrons directly into the conduction band. And molybdenum on the 24D site, so this is the irregular shaped octahedron, it is also a low energy defect and it injects electrons directly into the conduction band. What changes is the molybdenum on the 8B site shows a very different behavior. Its transition from the +1 charge state to the neutral charge state occurs below the conduction band minimum, meaning that electrons would have to be excited into the conduction band for this defect. So you have two different defect behaviors going on depending on if molybdenum goes on the 8B site or the 24D site. So we did some XAXS measurements to analyze the bond lengths around the molybdenum in the indium oxide matrix, and we kept coming out with a distance of about 2.05. And when we did our calculations for the neutral charge state, which would be this flat lines here, so for the purple and the green, what we found was that the bond lengths were about 2.09, 2.112, which didn't really fit with what was being seen in experiment. But when we looked at the +1 charge state, that's this charge state where the electron is no longer associated with the defect, it's actually zipping around in the conduction band minimum, and which are, of course, the lower energy numbers, these sloped lines here for the +1 and the +1 here for the purple and green, then they actually get much closer bond lengths compared to experiments, which is what is seen in the XAXS measurements. So what we can do is we put our defect in a supercell, and we've calculated the effect of this, and we can now unfold band structures to try and understand where these defect states fit within the band gap of the systems that we're interested in. So on the 24D site, molybdenum appears to be molybdenum 4+. It's formally D2, so 2 occupied D states in the middle of the band gap, and 1 unoccupied D state at the bottom of the conduction band, or just above it. On the 8B site, the picture is different. you have molybdenum, which is formally 3 plus D3. So 3 occupied D states and no unoccupied state at the bottom of the conduction band. But when you ionize these defects, or when that extra electron is actually zipping around in the conduction band, the picture becomes quite similar. 2 D states are pushed downwards in energy or stabilized, and the 1 D state becomes unoccupied and is pushed higher in energy. So this puzzled us for quite a while because we couldn't understand what was happening. And then as I was walking to teach an undergraduate tutorial in crystal field splitting and molecular orbital diagrams, it came to me, we could actually just analyze this quite simply with an MO diagram. So here we have the MO diagram for a molybdenum 06 octahedron trapped in the indium oxide matrix. Blue signifies the valence band and orange signifies the conduction band. So in your typical MO06 octahedron, you have 3 T2G states, which would be non-bonding. This is for the 8B site, so the regular octahedron. And that's what we see in the band structure, 3 electrons trapped on these 3 non-bonding T2G states. When we go to the 24D site, it's actually akin to having a small Jahn-Teller distortion. So you end up with 2 states being pushed down in energy and 1 state pushed upwards in energy. And of course, because this pushes up above the bottom of the conduction band, the electron falls off it and ends up in the bottom of the conduction band. And this is for the neutral charge state. But as we know from the XAXS, the bond lengths are actually shorter than what we found for this neutral charge state. So when you ionize this defect, when this electron has disappeared and is zipping around in the conduction band elsewhere, you get a bond contraction, which of course strengthens the Jahn-Teller distortion, stabilizing these 2 T2G states and destabilizing this unoccupied state, giving you the picture that we saw in our band structures. So this was very interesting. We were able to understand what was happening in the band structures using simple molecular orbital diagrams. But was this the real picture, or is this just an artifact of the level of theory that we're using, or did we make a mistake in the calculations? Could we believe our results? So we took the samples of molybdenum doped indium oxide and we went to our friends in IO9 in Diamond Light Source. So IO9 is the soft XPS and hard XPS beamline. We did our XAXS measurements, but what they showed was they clearly showed occupied D states in the band gap, confirming our calculations and confirming that molybdenum was in the 4+ oxidation state. We used inverse photoemission spectroscopy done by Tim Beale's group at Liverpool to find the presence of the unoccupied D states about 2.2 electron volts above the bottom of the conduction band. And we also used some XAS and XES measurements done by Professor Lewis Piper from the University of Warwick, who at the time was at Binghamton in the US, and I think he went to the Advanced Light Source in America to do these experiments, also showing these unoccupied states 2.2 eV above the bottom of the conduction band. So we have now the spectroscopic evidence that our model was correct and that we understood the behavior of molybdenum in these systems. What HackSpec also allows you to do is to zoom in on the bottom of the conduction band and look at the occupation of the bottom of that conduction band. And of course, the thing you have to remember is that the density of states of a system is basically the integration of the band structure. So the fact that the ITO has a higher peak intensity, but narrower than IMO, means that it supports IMO having a much curvier, more diffuse conduction band than ITO, which has a broader conduction band. So this is again more evidence for IMO having a higher mobility. So to look at the effect of these donor dopants on the system, we can look at the orbitals that make up these bands. So obviously these 2 molybdenum D states in the middle of the band gap, they're completely centered on the D orbitals of molybdenum. When we look at the bottom of the conduction band, the molybdenum dopant has no character whatsoever at the bottom of the conduction band. It's all indium and oxygen states mixing. And here at the unoccupied state, again, is centered solely on molybdenum and is an unoccupied D state. Whereas if we compare this non-interacting molybdenum state at the bottom of the conduction band with the tin dopant in the indium site, you can see that there's a lot of charge density around the tin, meaning that the tin and the indium are actually mixing and having a chemical interaction, which is what we believe is causing the issues with the effective mass of the ITO conduction band. So of course, my dean was very interested in seeing, could we basically get some interest from industry? So what we did was we carried out a number of durability tests on the doped indium oxides, and we showed that basically CVD grown IMO has basically the exact same performance as ITO in terms of its ability to weather general wear and tear. So there should be no barriers to the widespread adoption of IMO as a replacement to ITO. And the schematic or the cartoon of what's going on we're left with is that as you increase the doping concentration in IMO, because you have no interaction between the molybdenum D states and the bottom of the conduction band, the effective mass doesn't change, so you maintain a higher mobility. But as you increase the amount of tin in your system, you get increased mixing between the tin S states and the indium S states, and you end up with a broadening of the conduction band minimum, leading to tail off in performance and a lower mobility. So the lessons that we learned from this type of study was that IMO now is, we believe, superior to ITO, and thinner films of IMO can be used, which should give the same performance as thicker ITO. So we believe that this is actually a really big deal for industry, because you could use half of the indium to get the same performance as people are doing for ITO. But also you have this better IOR transparency, which is actually ideal for solar cells because you want to reduce the parasitic losses in the IOR in any devices. So what this taught us, going beyond just IMO and ITO, is that we have now design principles for finding dopants in other TCOs. So if you want a transition metal dopant with a donor D state that doesn't hybridize with the S states of the conduction band, and also you want that dopant to be a 1 electron donor, because you do not want to have ionized impurity scattering issues. You only want 1 excess donor per dopant. So then the open questions were, what is the optimal dopant for, say, tin dioxide or zinc oxide or gallium oxide? So that's what we went on to do next. So we were funded by Pilkington NSG, which is this very large glass company that I was mentioning. And they are the world's largest producer of fluorine-doped tin dioxide. And it's used for many of their ranges. They have different, you can get samples of their tech range, basically with any mobility up as far as a mobility of about 30 Siemens per centimeter per volt second. And the main dopants used in tin dioxide are fluorine, so FTO, or antimony, so ATO. And you can get pretty low resistivities, but both of these dopants are actually self-limiting. As you increase the carrier concentration, beyond a certain carrier concentration, you start to get a tail off in performance. And nobody had actually understood well what was going on in these systems, despite using them for over 50 years. So we did some analysis and we showed that for FTO, as you increase the carrier concentration, you actually start to get compensation by fluorine interstitials. And for ATO, you get Sb3+ formation because antimony 3+ segregates to the surfaces. And also you can get trapping of charge in oxygen vacancies near to antimony dopants. So now that we kind of understood the limitations of tin dioxide, we could go on and find out where they're more optimal dopants. So we did a screening, and we use our chemical knowledge. If we want a dopant that's going to have 1 extra electron, it's not going to be on the oxygen site, it's going to be a transition metal dopant, then your options are vanadium, niobium, or tantalum, because they're all 5+. Vanadium didn't work because the vanadium excess electrons stayed on vanadium, reducing the vanadium atom, making a colored tin dioxide. Niobium just wasn't a good dopant, but tantalum actually emerged as the ultimate dopant. Very low energy dopant, so very easy to incorporate. And what the band structure analysis told us was that the donor D states would sit very high above the very dispersed conduction band minimum, meaning that you would have the same type of mechanism as we saw for IMO. So again, we did a metadata analysis looking at all of the previous papers that had ever been published on, say, tantalum doped tin dioxide, which my collaborators continue to call Tato, because Tato is the name of a crisp company in Ireland, and they think this is hilarious. But Tato is found to outperform ATO in terms of mobilities and conductivities, and had been in the couple of papers that were published on this in the literature. And again, these results have been ignored because people couldn't explain them, and they assumed they must have been measurement faults. So again, Tato displays higher transparency in the IOR, which can be linked to the plasma energy. So we have the exact same doping mechanism at play here. And again, this helps to bring tin dioxide to higher mobilities and to higher transparencies, meaning that we can use it for more and more devices. But we weren't limited just to looking at tantalum. We also looked at tungsten as a dopant. And we did this in collaboration with a group in Japan. And what our calculations showed is that tungsten is a very low energy dopant. It injects electrons directly into the conduction band. It forms as tungsten 5+, not as tungsten 6+. And in fact, the samples showed mobilities as high as 136 Siemens squared per volt second, which would be a world record for doped tin dioxide. Again, more transparency in the IOR, so exact same mechanism as previously. Again, band structures show you very similar picture. One occupied D state in the middle of the band gap, meaning that's why it's tungsten 5+. The other unoccupied D states are high up in the bottom of the conduction band, way away from the conduction band minimum, no interaction, so maintaining the high mobility. And recently we showed in a paper that was actually just accepted this morning in Cell Reports Physical Science that silicon acts as a similar type of dopant in gallium oxide. So gallium oxide is an oxide that is probably the sexiest oxide in the world right now, because it has a 4.9 electron volt band gap, so a huge band gap. And it's used for, or they're trying to use it for power electronics, because the bigger a band gap in a power electronic system, the better the breakdown field, the more power you can put through it, and the thinner the device you can make. So this is a material that everyone is interested in at the moment. But up until this paper, people had only ever managed to get about 700 Siemens per centimeter of a conductivity. And we have shown that that was simply a limitation of how they were growing the system, and that these PLD grown films have reached 2,500 Siemens per centimeter. So this actually pushes this material beyond even just power electronics, but now can be thought of as a transparent glass, just like tin dioxide and doped indium oxide, and therefore you can have it as an ultra wide band gap transparent electrode. So this is going to open up new avenues for gallium oxide research. But what we showed using our same band structure analysis is that the silicon states sit high above the bottom of the conduction band, and they do not mix with the bottom of the conduction band, meaning that silicon actually acts just like those transition metal dopants did in those other systems that I was showing. So again, nice, lots of transparency in the IOR, same type of mechanism. And even better, we could modulate the work functions of the systems from about 3.2 eV to about 4 EV, meaning that they're actually perfect for organic electronics, because the typical TCOs have work functions from about 4.5 to 5 EV, which mean they're not ideally placed for a lot of organic semiconductors. So this now brings this high conductivity, high mobility, brings these systems more in line with being used in organic electronics. And the last thing I will leave you with is the idea of this remote dopant, as we call it, where you have this dopant state where it is resonant in the defect. The defect is resonant in the conduction band far away from the conduction band minimum. That is what we would call an energetic separation. But in the case of barium stannate, which is another new transparent conducting oxide, lanthanum dopes on the barium site, and the lanthanum states are very high above the bottom of the conduction band. So you have that energetic separation between the conductional minimum and the lowest lanthanum states. But also you have the spatial separation, because the lanthanum is on the barium site, which sits in this hole between these octahedra, whereas the tin oxygen network is the 3D corner sharing network of how the electrons move. So you don't even just have this energetic separation, you actually have a spatial separation between the scattering ion and the electrons that are zipping around in your material. And what this gives you is it screens the ionized impurity scattering, making the mobility even higher. And this explains why barium stannate has the highest mobility of all TCOs at 320. It's simply the same doping mechanism that we only discovered last year and the year before, but can actually be used to explain the high performance of lanthanum doped barium stannate. So to conclude, I hope I've shown you that resonant dopants provide higher mobilities, higher conductivities, and better transparency, especially in the IOR, and that for any study going forward, if you're trying to design high mobility systems, especially in oxides, conventional doping choices can be wise, but now should always be checked against potential resonant dopants. So simply just doing the standard one to the right in the periodic table will give you a result, but will it give you the best result? And we think that going forward now, everyone should screen nearly every dopant just to make sure. So I also hope that I've explained that if you have good theory, good experiment, and good characterization, that basically you should be able to explain most experimental observations if you build the right team. So to acknowledge, I need to acknowledge some people in my group: Adam Jackson, Winnie Leung, Rob Palgrave, Ben Parrott, and Rob Perry. Ben Williamson, who did most of these calculations, is now a postdoc in NTNU in Trondheim. Sanjay Sathasivam, who grew all the samples, working for Professor Carmelt and Professor Park at UCL. Tim Veal's team at Liverpool, who did a lot of the characterization. The guys at NSG, who funded the work. And the people who did a lot of the characterization at synchrotrons. Anna Raguz, who's now at UCL. Tianlin Li, who runs the diamond ion beamline. And Lewis Piper, who's actually now at Warwick. He just moved last year. And also, these would not have been possible without access to all of the compute resources. So Legion and Grace are UCL supercomputers, and Thomas, which is a MMM Hub sponsored machine, and of course Archer and Archer 2, which we gain access through the Materials Chemistry Consortium, and all of the funding bodies who make all of this research and all of this computer time possible. And thank you for your attention, and I'm happy to take any questions.
Thank you very much, Professor Scanlon, on your the presentation of your very great work. We have about 10 minutes for questions, because Professor Scanlon has other work to do later. So if you have any questions, please raise your hands. Vangelis, please go ahead.
Yeah. So thank you very much, David. It was excellent, a very, very nice, very interesting presentation. So I'm not really expert in the field, so just a couple of questions which are more generic. The first is, you discussed very shortly this meta-analysis that you have done.
Yeah.
Can you please comment a little bit on that? I mean, I assume that previous studies also might use different functionals or different unit cells. So how do you take into account such differences?
So the meta-analysis was all experimental.
Okay, so it's based on the experimental data.
Basically on the experimental, because there were, when we had originally started this molybdenum doped indium oxide stuff, we found 30 papers, and 27 of those papers had found that IMO was better than ITO, but they were being published in journals that people wouldn't even see these papers in, right? And because I think reviewers and people in the field were so scared of a new idea, and because it didn't have an explanation, they just didn't believe it. So they assumed it was wrong. That's the only conclusion I can come to, that the field was just not ready for something that was saying that ITO wasn't as good as a material. But yeah, if it had been calculation data, that would have been a lot. more difficult to do. There was only one paper in the field. It was actually a PRL saying that molybdenum was 6+, but obviously our calculations and our experiments showed that that one was wrong. That was by Julia Medvedeva, who's at the University of Missouri. We've discussed since then, but she was using GGA plus U, which was a reasonable functional at the time when they did the study back in 2006, but you couldn't get the right answer with that functional.
Okay, so it was a matter of the functional. Yeah, okay.
Yeah.
And just let's say a follow-up now. So I would assume, especially for the defects, that you need large systems in order to, let's say, accurately predict the properties. So can you deal with such large systems?
So we typically try to have a supercell that is more than 10 angstroms in each direction, because then you don't get issues of periodic images for charge defects interacting with one another. So for these molybdenum doped indium oxide systems, we did them in an 80 atom supercell and with hybrid DFT, so very expensive because we had to use a lot of K points as well to deal with the band dispersion. But we tested 320 atom supercells to make sure that we were getting similar answers. That basically took an awful lot of time, even on the UK's supercomputing system. For the tin dioxide, we used 96 atom cells and 72 atom cells. And for the barium stannite, I did them on 135 atom cells because, 135 atom cells.
But in real systems, you might have also large scale defects, right?
Yeah, so we haven't been able to look at, these are more point defects. We haven't been able to look at line defects and things like that. They're much more involved. And we've submitted a grant to now understand how these defects behave in the presence of grain boundaries and dislocations. My PhD supervisor actually wrote a code to generate grain boundaries, which is still being used, even though he wrote it 30 years ago. So we're going to adapt that to make it more modern and make it actually write it in Python rather than what it's written in at the moment. So we're quite excited because now that computers are becoming bigger and stronger and more powerful, we think we're going to be able to actually dig even further into how these defects behave in real systems.
Great. Thanks again.
Thanks very much, Magnalis.
Professor Alexandra?
Yeah, I think partly address what I was going to ask you, David. I mean, I'm not an expert at all in this, but I was just wondering what is the computational resources that you used and what would be needed for the next iteration. I mean, as you said, now, we have bigger computers. So what kind of systems do you now have with the exascale era?
So this is a very good question, and it's one that we are struggling with in the UK right now as well. As I was saying to Stelios before we started, the UK bought a new supercomputer in 2019 for 79 million. It's a Cray supercomputer, 128 cores per node, 256 gigabytes per node. And they
is this at the EPSC?
EPSRC sponsored it. It's held by the EPCC in Edinburgh. That's where it's based. The machine, because of the UK's Brexit ideology, they only time tested or did scaling tests for UK-based codes, and they didn't time test the code that we use, which is VASP, which is obviously an Austrian code and probably the most used code in the world for our types of calculations. So the machine that they bought shows great speed up for the codes that they tested, but it actually slows VASP down compared to our last supercomputer. The problem is 60% of the use of the machine is VASP. So there are a large number of us who are very annoyed. At UCL, we have been buying GPU accelerated nodes, and we can, on 4 nodes and 4 GPUs, we can do the same amount of work, 4 cores and 4 GPUs. We can do the same amount of work as 1,000 cores on the Archer 2 machine, this new supercomputer. So we've realized that if they just bought a system of nodes with GPUs, they could have come in at £40 million cheaper and had a faster machine. So that there's there's a chance that there's going to be a question in Parliament over this.
Oh.
So yeah.
Okay, interesting.
So I would like to say that the UK is well placed to know what to do going forward, but we don't know what we're doing going forward. We know what we would like to be able to achieve, and we think that we're in danger of falling behind the rest of Europe in terms of how competitive we are, because the compute resource we have is probably not going to cut it. The new machine that came online this year in January, and it is already pretty much full. So there's no room for growth either. The machine is slower and it's full already.
Actually, this is very surprising because everybody now is having accelerators. So it is very surprising that your new machine is of this architecture alone.
Yes, yeah. I think I can't understand the decisions that were made. And we were not party to them either. They were not made in a public environment. They were done by a small select committee, and the community didn't really have much of a say. So what I would say is make sure you do take note of what your community needs.
Oh yeah,
moving forward.
we do.
Yeah.
We certainly do, yes. But we also push for new technology because, as you know, we all do it. Researchers are very reluctant to invest time in code development. So you have to really push the community for the new hardware and the new technology. So I think this is very important. I mean, to take, for example, accelerator capabilities are going to be crucial to get the kind of science that one has to do.
So our experience currently on the test that we're doing at the moment is that accelerators are really awesome when it comes to large systems. Not so brilliant for small systems, but then again, you probably don't need them for the smaller systems. But for the larger systems, it really helps our workflow. So we're very excited about that dimension. And however, we don't know how long it will take the UK to go in that direction, but our university is currently going in that direction.
Great. Thanks very much.
Thank you very much.
Okay, we have one final question, Mac. If you can ask Professor Scanlon.
Okay. Hello.
Hello.
Yes. Basically, I tried to share my video. It's not going through, and I want to know mostly because from the topic, I understand that the TCO, the ITO, was the most industrial standard for the TCO in many optoelectronic applications. Which is the ITO market share was 93% in 2013. Now, yes, I want to know now how the situation in 2021 to 2022, how it is grow, is it about 100% now, is it or it decreased? That's what I want to know.
So the market share hasn't changed because the companies are so slow to move to something new. What we're seeing is in lab-based research, the amount of studies that are done using these remote resonant dopants that we've been predicting and explaining has now increased hugely. But again, the industry is very slow to change. Because, just because one deposition method for one material works, it might not work for the next dopant. So if you're going to change your entire industrial setup to produce a new doped thin film, you have to be able to do it in the same way you were doing it, or you change the setup of your factory completely. So we are hoping that things are moving in the right direction. In lab-based stuff that we can see is moving in the right direction, but yeah, so far industry hasn't changed.
Okay, so now for the prediction, and that means for the next decade is going to increase to the 100%.
Yeah, possibly. I mean, our demand for these devices is not getting any smaller. You know, everyone wants to have a phone. Some people have 2 phones, some people have 3.
Yes, basically me and I have 3 phones. Yeah, so it's a nice joining the topic because I'm no word much familiar to this one, which is the chemistry. But I'm a student. I'm 20 years, and I enjoy the session. So I feel it's a more great opportunity for me to know much about how the equipment of the TCO in the ITO market look. That's why I joined. But this is nice and thank you and appreciate that.
Thank you very much.
Okay.
Thank you, Mac. And what's more,
Thank you, Matt.
okay,
What's more,
we're going to have to close this session in a bit because Professor Scanlon has to go.
we're going to
I
have
would like to thank Professor
close this
Scanlon
session
for his presentation. And thank you everyone else for joining. And we hope to see you all in another session in the future. Thanks again, Professor Scanlon, and we'll see everyone again in another seminar.
Thanks
Bye,
very
everyone.
much. Bye-bye.
Thank you very much. Bye. Bye.
Okay. One question to